Thank you very much for watching this video. As you may know, I was supposed to perform a live demonstration of this Kendrick analysis during our annual workshop at the ASMS last June, but we had so many things to go over, we had to postpone this demonstration. And I said later that I would um, organize one of our informal virtual online meetings doing that demonstration, but you know how it is. We all are busy, and I am busy, and I didn't have enough time to prepare for that presentation. So I'm trying today a third way, simply recording myself and just going over the slides I presented last August during the the materials symposium organized by Waters at Pittsburgh. Um, so during that symposium, I presented some slides about this analysis, how to build these plots and what to expect from them, what type of information we can expect and we can get from this Kendrick plots. So I will go over the slides today, and if you have any questions or if you have any comments or any ideas of things to develop, things to implement, feel free to send me a message uh, by email or via our LinkedIn group. Okay, so very briefly, the idea behind these plots is just that we all know that the main drawback of mass spec, and especially high resolution mass spectrometry, is just the number of peaks that we are facing in every single mass spectrum. If you look at any very basic, very typical mass spectrum of a polymer, you will have hundreds or thousands or sometimes millions of peaks to potentially assign or at least understand. And so if you want to look at data manually, kind of old-fashioned way, you basically need to just explore the mass spectrum, zoom in, zoom out constantly, trying to understand, trying to assign these peaks, and search for potentially isobaric interferences. So it can be a very long process, and it's just impossible to do that all the time for every single sample. You may think that exploring data manually today, I mean, like these days, sounds a bit stupid or a bit old-fashioned in an AI-powered world, but I think there is still some value looking at data by yourself and not always relying completely or exclusively on programs. It's still good to know what you have and what type of data you're generating before blindly trusting programs to assign peaks and to compare data sets for you without even looking at a single mass spectrum. So I at least I spend some time still looking at data myself, even if I rely on programs afterwards. Right. So what I'm trying to show today is basically how to switch from this view, this mass spectrum view, to this kind of 2D map, which is displaying useful or information-rich alignments that reveal um, information about the sample composition or about the series that you may have in your mass spectrum. So I'll present very briefly a few concepts before switching to a bunch of examples of application of this mapping technique. So briefly about the let's say nomenclatures, right? Terms. We all are using the term mass defect in our papers. The thing is, it's probably a mistake because we don't really deal with mass defects when we are using these Kendrick plots. Um, a mass defect, there are actually two definitions for mass defect. We can consider the physical or nuclear mass defect, which would be the difference between the mass of the nucleus and the sum of the mass of the nucleons, right? The mass of the nucleus is slightly lower than the sum of the mass of the nucleons because you have a binding energy. That's the physical nuclear mass defect. The chemical mass defect, it follows the same trend as the physical mass defect, but its definition is different. We define a chemical mass defect as the difference between the uh, exact mass of an atom or molecule and its nominal mass, right? In the IUPAC system, we are defining the mass of carbon-12 in its ground state as 12 Dalton or mass units. And from that reference, every other mass of every other element or molecule or moiety is a non-integer, right? H, O, or molecule, they all have a non-integer mass. It is also linked to the binding energy and the fact that the molecule has a lower mass than the sum of the mass of its components because of binding energy. The thing is, to calculate a mass defect, you basically need to know the composition of the molecule. I'm showing an example here for PMMA 26 mer. Its m over z, its exact m over z, can be decomposed into the nominal m over z and that mass defect or mass excess. But to know that nominal mass, to know this value, this red value here, you need to know the composition. So to calculate a mass defect, you need to know in advance the composition of a molecule, which sounds a bit stupid for mass spec. If you know everything about your sample, and if you know the composition of every single molecule and ion in your mix or in your data, you don't really need to use mass spec anymore. So that's why I call that mass defect something which is composition dependent. Again, to calculate a true mass defect, you need to know the composition in advance. So it's either we all have an FTICR system available with a mass error at 1 ppb to assign everything for sure, or we do something else. And what we do, and what we all do in our papers when we talk about Kendrick plots, and we claim that we are doing KMD, Kendrick mass defect, what we actually do is a KFM, a Kendrick fractional mass. What we are doing is the calculating the fractional part of mass of m over z. You will probably see in all these papers, and mine included, that we always report that mass defect being the difference between the exact m over z and its rounded value. We have m over z minus round m over z. This is no mass defect. This is the fractional mass, the fractional part of m over z. The two are kind of related, this fractional mass and the mass defect. You can see it's not that different. There is only, how to call that? The one is simply an aliased version of the other. You only have one unity between the mass defect and the fractional mass. This part is the same. So the information that they convey is not that different. But again, it's not the same definition. So we are supposed to use proper terms. So I am trying to avoid in my papers now using the term mass defect when what we are actually calculating is a fractional part of mass. And at least this value, this variable is composition independent because I don't need to know the composition anymore. What I need to do is simply calculate m over z minus round m over z. This requires only m over z, which is what my mass spec is giving me. So I need no information in advance beforehand to calculate this value, fractional part of m over z, which is what we call wrongly in our papers mass defect. Anyway, if you plot that fractional part of m over z or aka mass defect versus M over Z, you are creating this new 2D map. I call this 2D. It can be 2D or 3D, depends on how you actually call the mass spectrum itself. It can be a mass spectrum can be already seen as a 2D plot with M over Z in the x-axis and the abundance along the y-axis, or you can simply say that the main information, the most important information in the mass spectrum is actually along the x-axis. It's M over Z. So a mass spec can actually be just a 1D plot. The information that you really care about is along the x-axis. This one is secondary axis. So again, you can say that you turn a 1D into a 2D or a 2D into a 3D. The idea that you simply add one dimension to the mass spectrum, which is this fractional part of M over Z, and that is producing this beautiful map which clearly shows alignments, right, from that mass spectrum, from a polymer sample, which of course display oligomers with some patterns. The patterns are clearly visible in this new map, right, through these alignments. One alignment here, one alignment here. About that second dimension, that new dimension I'm adding here, the fractional mass, as known as mass defect, it is of course non-orthogonal to mass spec, because what we display here is just the fractional part of M over Z, so it is directly linked to M over Z. So the y and x axis are related to each other. They're not orthogonal, as would be an IMS separation or LC separation. So this is not orthogonal. It is still mass spec. But the great power of this technique is that it's, as I said before, it's a composition independent. I do not need to know anything about my molecule, my ions. I don't need to assign anything beforehand to produce this plot from a mass spectrum. I just do this simple calculation, M over Z minus random over Z, and I got this map, which can be produced in milliseconds. I'm actually trying to implement this this new way of displaying mass spectral data on the fly. I'm trying to discuss with manufacturers for them to implement this simple switch between mass spec and KMD plot, or let's call this K plot, just Kendrick plots without any mass defect information, so we don't do any mistake in the terms. So this is very simple to generate. Again, it needs nothing. It needs no preprocessing whatsoever. Just run M over Z minus M over Z, and you have your new y-axis in the terms in milliseconds. So for now, I'm talking about mass using the IUPAC definitions, which means that as we all use like daily, we say that the mass of carbon-12 in the ground state is 12, and from that reference, every other mass of every other element, ion, molecule, moiety, is a non-integer. But this is a convention. This is a reference. This is a definition. I mean, some people chose that the mass of carbon-12 is 12, but that can be changed. Actually, if I remember correctly, I think in the past, the reference was oxygen. I think for a while, we were using the mass of oxygen as a reference as 16, and from that mass, everything else was evaluated. Now we're using carbon-12, but again, this can be changed. So I can just claim that my reference is no longer carbon, but it's something else. For example, here, I can say that my reference becomes MMA. I say I choose that the mass of MMA, so the mass of C5H8O2 becomes 100. It's 100.0524 in the IUPAC scale, but in my new scale, in my new basis, it's 100. And from that new reference, I can recalculate every other mass of every other element, right? And so now carbon-12 becomes also non-integer, and everything else has a new value. This is what Kendrick proposed a long time ago when he chose the mass of CH2 methylene as a new reference. He said that, okay, I want methylene to be 14, and I recalculate every other mass based on this new reference. It's actually a funny thing that in this very first paper of Kendrick, this actually looks weird to me. I don't know why he said that it should be 14.0000, because this is implying that it actually, you may have other numbers after the fourth decimal number here. It's not true. It's just 14. It's a integer, pure integer. There is no decimal point or decimal value after. You just say that CH2 is 14. I say here that MMA is 100. No 0.000, just 100, pure integer. Okay, and so to calculate the mass of other elements or other molecules using that new reference, it's the level 0 of mathematics. What I do is simply a cross multiplication. Okay. When you have your M over Z value, which is evaluated using R as a reference, well, now I want to have round R as a reference. So my new M over Z value, my Kendrick M over Z value, is simply round R by M over Z over R. That's just the simplest calculation ever, just a cross multiplication. M over Z by round R over R. And that's giving me the new value of M over Z. I rescale my mass values. And so I get a new plot, of course, because now my y-axis, the values of the y-axis are impacted. I'm rescaling the mass. So the fractional mass, ICA mass defect are impacted. In the IOPAC scale, I got these two alignments, both being oblique, but that series here is actually PMMA. I'm sorry, it's PMMA. So if I'm using MMA as a reference, I say that MMA becomes 100. So that means you can add as many MMA moiety as you want to a molecule. You will add 100 to the mass. There is no more decimal parts variation. You just add the mass by 100. You can see here PMMA 28 mer to PMMA 29 mer. I'm simply adding 100. The fractional mass is not impacted. While it was impacted in the IOPAC scale, because here you're adding 100.0524. So both the integer part of the mass and the fractional part of the mass are impacted. But in my new reference, I just add 100. There is no more variation of the fractional mass. That means that in the plot itself, PMMA becomes a flat line. There is no more variation when you add MMA moiety to the molecules. When the dP is increasing, the mass defect or the fractional mass doesn't change. So overall, the PMMA series is a flat line. The only value that you have here, the only thing which impacts the value of the fractional mass are basically the N groups and the ions. In that case, I think it was a PMMA with silver, if I remember properly. So the mass that you have along the y-axis is just the fractional mass of silver and the N groups, and the rest is just a flat line. Okay. And the same if I'm using another rescaling unit. In that case, that mass spectrum is a blend of PMMA and polycarbonate. So if I'm using now the mass of that polycarbonate as a new reference, so I rescale that mass to the closest integer. Now the PC itself is a flat line, and the PMMA becomes another oblique line. So you can visualize in a second that you have a PMMA here and a PC here, just by rescaling that plot, which again needs nothing special to be generated. You only do that from the mass spectrum without any information. Okay. All right. So this is the, let's say, the traditional way to do this these Kendrick plots. There is only one drawback here. There's one limiting point here, is that you basically generate only, sorry, you generate only one plot per R. So you make only one plot per moiety, per reference. I make one plot for PMMA, I make one plot for PC. But I cannot do anything more here. From this plot, from that plot, I cannot do anything anymore. Only one plot per R, per rescaling unit, because of this definition. So only one plot per R. So a few years ago, actually, we said that there is no real reason to force that rescaling unit to be only round of R. Here we say that if I use the MMA example, MMA, which is 100.0524 in the IOPAC unit, IOPAC scale, becomes 100. But why 100 only? There is no reason to have only one value of for the rescaling. I can say that MMA becomes 98, or becomes 50, or becomes 1,253. It can be anything, as long as it is an integer to remove the variation of the fractional part of mass, to have a flat line. It can be any integer. It doesn't have to be only round R, or for MMA only 100. It can be anything. So we said that we propose a new definition of this Kendrick over Z, of this rescaling. We don't have round R anymore, but we have X, which can be any integer. And for a good measure, we also added another value, Z, used to either counterbalance the Z of the M over Z, so to remove the charge from the equation, or in combination with X, having even more values of rescaling. So just look at these values Z and X as just the same thing. The main idea is just to say there is no reason to have only run R as a rescaling value. It can be any integer. And just by saying that, it means that now I can generate as many plots as I want. It doesn't have to be only one plot per R. It can be as many as I want. It can be as many integers in the world, which is unlimited. So an example here, very briefly, again from my PMMA mass spectrum, sorry, PMMA and PC mass spectrum. I turn into this first map by rescaling with the, let's say, the old-fashioned way, just MMA becomes 100. I'm calling this a static rescaling because there's only one plot possible, and my PMMA appears as a flat line. Good. But now I'm using my new definition where I can use other values than run of R to rescale my mass. Here I'm using 299. Okay, so actually combination of X and Z, 149.5 and 2, which means overall my MMA mass is rescaled from 100.0524 to 299. So I chose that MMA becomes 299, and from this, every other mass is calculated as normal. Doing that, you have this new interesting plot where you see at least two lines, two flat lines, one here, and maybe something here too. So just by changing my rescaling value, without doing anything else, I can reveal at a glance that I have at least two MMA series here, two PMMA series here, 1 and 2, which were actually overlapping in the initial plot. It is impossible to see that there is another series here at a glance. Just by rescaling, keeping the full scale along the y-axis, I can show that I have 1 and 2 series, and maybe 3 here. Or I can rescale with another value. I'm using here 104. So MMA 100.0524 in the IOPAC scale becomes 104. That's my choice. And doing that, I actually At the same time, I separate the MMA1, MMA2 series, and I am also expanding the patterns. This is the carbon 12 series. So all these points are the monoisotopic peaks of the PMMA series. And this is carbon 13, 13.1, 13.2, 13.3. So in other words, you look here at the isotopic pattern of PMMA. So using wisely, carefully this value of x to rescale the mass, you get this plot, which is revealing at a glance that you have two PMMA series, and it's also revealing the patterns of isotopes. Or I'm using here 98, which has the multiple advantage that it's aligning, let's say, horizontally PMMA and also the PC, kind of. So you don't have this oblique and kind of cut or folded alignments. Now everything fits within this fractional this y-axis range. There is no more aliasing. Everything is more or less flat. It's revealing the PMMA series 1 and 2. It's revealing that you also have actually two PC series here, one PC series here, another one here. So just by rescaling my MMA, instead of using 100, I'm using 98. I can show that I have two different types of polymers in my mass spectrum, PMMA and PC, that I have at least two series per polymer. So for PMMA and PC, there are two series for each. And I can also see at a glance the patterns of isotopes. So from this, where everything is more or less overlapped and hard to see at a glance, to this, where everything is on the contrary, expanded, revealed, and I think you have much more information available at a glance here than here, just by choosing wisely that rescaling value. I said at the beginning that you need no information whatsoever to generate these plots. It is true, and it is so true that we actually don't need to know the monomer itself in advance. Right here, I used MMA because I knew I had a PMMA in my sample, but I don't need to know that because I can use the plot to calculate the mass of the repeating moiety or to evaluate, to guess the nature of the polymer. The idea is very simple. It's that you have a list of monomers here, and you can see that for each monomer you have a specific mass, of course, a specific mass of the monomer, and each monomer has its own ratio round R over R. Each monomer has its unique ratio, which means that each polymer has its unique slope in the plot. If you have a plot from a mass spectrum of a mix of THF, PLA, PGA, PVP, PCl, you will have as many lines in the plot, which each line with its own slope, each slope corresponding to a specific polymer, because of this ratio, which is unique to each polymer. What I can do is when I'm facing an unknown sample, I have this pre-made list of known monomers, and I am simply rotating my plot to screen over these ratios. What I'm doing here is just I'm changing the ratio. I'm changing my ratio here. I'm screening my known monomers until I have something clearly horizontal, like this. Here it's horizontal, and my program tells me that can be the slope of poly-THF or PA69. If I keep turning my plot, you will have other possibilities. But of course, this is no more flat, so this is, of course, no PTFE or no PVP or and so on. It's flat here. It can be poly-THF or PA69. To choose between the two, I can test them. I'm testing PA69 here. I got that plot. That's my static plot. So 304 becomes 304.2362 becomes 304. That's my static plot. I can rescale my plot in a dynamic way. I got that mess. Everything is spread seemingly randomly. So this is no PA69 for sure. So I tried the other one. I'm trying THF. I got this plot, basic plot, 62.0575 becomes 72. Sorry, 72.0575 becomes 72. And I rescale dynamic plot, and I got this. This is clearly the plot of a poly THF rescaled using 74. You still have clear visual alignments of series. So here, just by this rotation of my plot, I have been able to find out that it is the mass spectrum of the poly THF without having to look at the mass at the value of m over z in the spectrum itself and calculate the difference. So just by screening through this pre-made list of monomers. Another way to do that without any list of monomers, like this is really an de novo evaluation of the monomers in my mass spectrum, is doing a double rotation. I got this plot. This is using the IUPAC scale of mass, and I have clearly a polymer here because I have this alignment, but I don't know which polymer I'm looking at. I'm doing a first rotation to align the plot horizontally. Here we are. Sorry. Here we are. I got my first alignment here. What I'm doing next is I keep rotating the plot. I keep changing my ratio here. The plot is rotating until I find a second clear alignment of series. Here we are. You got this. You have clearly series being lining up horizontally. And you can see here that the program has been able to evaluate that mass 72.0716, which is close enough from the mass of THF. So once more, using this trick of a double rotation, first alignment, second alignment, you can evaluate the mass of the monomer that you have in this mass spectrum without having to look at the mass in the mass spectrum, without having to do any calculation of moiety being repeated or whatever. Just graphically play with the alignment and either use a list of known monomers or use this double rotation technique to estimate potential mass of monomers. So in that case, the method is absolutely de novo. I really need nothing about the sample in advance. I can just rely on the graphics, rely on the alignments to get all the information I want from that sample. All right, that's all for the concepts. I just want to go over a bunch of examples to see how this plot and how this rescaling, this dynamic rescaling, when I choose other value than the 1R to calculate my mass, how this can be used in for real data sets. All right, so the easiest case possible. This is the MALDI HRMS spectrum of a PEO, of a blend of PEOs. All right, so that's my mass spectrum. You can see that you have multiple series overlapping. And this is my Kendrick plot using the IUPAC scale. So carbon 12 is 12, and PEO EO is 44.02621. So my PEOs, when you increase the number of units in the chain, you have an increase of m over z, and you also have a variation of the fractional mass. So the PEO lines up along an oblique direction. Now I rescale that map. I rescale my m over z using EO as my new reference. So EO becomes 44. The mass of EO is now 44. That's my choice. Doing that, there is no more variation of the fractional mass of PEOs. So my PEOs appear as flat lines in the plot. And at a glance, you can see that you have at least 3 types of PEOs in the mass spectrum. And once you assign this series, you know that actually one is just a HOH PEO, like a PEG. Another one has one fatty acid at the end. The other one has two fatty acids, one at each end group. So at least that's, let's say, the normal analysis that we used to do in our papers. From this mass spectrum to that plot, you already have a clear increase, clear gain of information at a glance, okay? But you can go a bit further using this new formula to do what I call this dynamic plot. So now I say that EO is no longer 44.02621. It's no longer 44. I say it's 87, right? Because again, I can choose whatever I want. There is no reason to use only 44. It can be anything you want. And if this value is chosen carefully, as here I'm using 87, I can reveal at a glance that my MALDI mass spectrum is containing not 1, not 3, but 1, 2, 3, 4, 5, 6, 7, at least 7 PO series. You have clearly 7 groups of point, and each group corresponds to a specific PO series. And again, if you spend time, once you have the separation, I can isolate the series one by one to retrieve the corresponding M over Z and try to assign the end groups. And doing that, you can find that actually one is, again, the PEG. Those two are what I call the monofunctionalized series, and they actually are monosterate, monopalmitate. And these three series are just difunctionalized PEO with two stearates or two palmitates or a combination of both as in groups. So 1, 2, 3, 4, 5, 6, and actually probably 7 here, slightly overlapping, but still, again, from that mass spectrum to that map, it takes 1 millisecond or less to compute that map, and you can clearly see the gain of information, the gain of information that you get in a second just by playing with that rescaling of M over Z. Another example here. This is a PyDart MS data of a PVDF sample. That's my initial mass spectrum. And this is my, let's say, static Kendrick plot using HF to rescale the mass. I got something more or less flat, right? Because I'm using HF. So, okay, maybe the points are kind of HF spaced, but there are two things to notice here. First, there is an awful waste of space, right? Like all this part of the plot I put in green on top and bottom, this is empty. So it's useless. It's not used by this plot, and it's a waste of space. They should be I mean, we have a lot of room for more separation of series here, which is unused when you use that basic rescaling by HF. And if you zoom around that cloud of points here, you got this messy, fuzzy cluster. There is no clear alignment because the mass spec maybe doesn't have enough resolution or good enough, but not enough to separate series as you would have maybe with an FTICR system. So you have a fuzzy cloud of points when you zoom around the cluster, and you have a waste of space because all these parts are useless. The plot is, you use only maybe 10% of the plot here. So instead, what I can do is rescaling using something else than 20. Okay, HF IUPAC mass 20.0062. Static transformation 20, but that's why 20? It can be something else. So here I'm using 19. I chose that HF, the mass of HF becomes 19. And doing that, you now got that interesting plot where the entirety of the space along the y-axis is now used. I'm spreading the series along the entire y-axis. You don't have this packed condensed cluster anymore. You have series clearly along the whole axis. And now you can see at the glance, you can see at full scale that you have series. It's a bit wavy, again, because the mass spec itself probably lacks a bit of resolution or accuracy, but you can still see that you have series, and these series are actually HF series. What you see here, for example, starting from that big dot here, those are actually consecutive losses of HF. This is one PVDF oligomer, which is expelling HF neutrals step by step during the PyDart process. So overall, by changing that rescaling mass from 20 to 19, from static to dynamic, you take advantage of the entire y-axis width, and you also reveal alignments at a glance that are completely lost or completely overlapping in the static plot. All right. Okay, another example here. This is a PyGCMS of a PP sample, polypropylene sample, mass spectrum, rescaling by CH2, the static one, 14.0157 to 14, and rescaling using 16, the new definition, dynamic definition, using 16. You got this interesting expansion, spreading of points along the y-axis. But if you look at the series, you have this weird alternation, big dot, medium size, big, small, medium, big, small, medium. And it's clearly not aligned along a flat, it's not lining up horizontally. You have a bit of waviness here. So that's a weird plot, but it makes complete sense because I have a PP here, which is a C3H6 monomer, not CH2. So now what's happening if I'm using a C3H6 rescaling unit? Look at these two plots, the static CH2 versus static C3H6. The same thing. So that old definition of conic mass, if you use CH2 or if you use propylene, there is no difference in the plot. But now, if I'm using that new definition, the dynamic plot, using 41 to rescale, so C3H6, which is normally 42.0470, becomes 41. Now this plot is revealing something very interesting. It's showing that you have at least 3 series of PP in this mass spectrum. So the two static plots are the same using CH2 or propylene, but the dynamic plots are different. And this one is revealing a lot of information that would be overlapped, that would be lost in the mass spectrum, and that is also not clearly revealed by this plot. So this one, propylene with a carefully chosen rescaling mass, is revealing that you have 3 PP series in that mass spectrum. Okay, this is the MALDI HRMS of a copolymer, an EVA copolymer. Mass spectrum, bit of a mess. That's my first Kendrick plot, rescaling using ethylene, okay, from 28.0313 to 28. That's my static plot. This plot is still very useful because you can easily separate the EVA series from the noise. So that map can be very useful to denoise your mass spectrum. And I want to show this example. It's very important because you should look at these plots not as static frozen pictures, but as dynamic interactive tools. If you have the proper program, if your software that you use to make these plots is good enough, you should be able to extract, to select, to isolate these points from that plot and process these points sequentially. Okay, here I got that plot. It's separating the noise from the EVA. My program that I coded in-house, my own program, Kendo or Bogbunja. In this program, I can select, I can draw a shape around that EVA copolymer, around these points, which are of course EVA copolymers. I draw a shape here, I select these points, I extract these points from that plot. So I remove the noise. and I got now a denoised MS data from which I can use another rescaling value. So here I'm using 202. So my ethylene mass, which is normally 28, becomes 202. So I have a massive rescaling. I have a massive expansion along the y-axis. And that rescaling is actually good to separate the isotopes. I am spreading this series so differently from this plot that now all my carbon-12 peaks are clustered, are packed into this single cloud of points here. And those 4 clouds are simply the carbon-13 1, 2, and 3. Those are the isotopes of that first monoatomic cloud. So again, here I can select these points. I can draw a shape around to select these points, extract them from the plot, and process them using another value of rescaling. Step by step, I rescale, I spread, I separate, I isolate, and again, again, and again. So here I got that last plot from these 12C peaks only, and I can rescale a third time. I'm using here 56 to rescale, and you can reveal this beautiful elliptic-like shape, which is typical of a copolymer, each line being polyethylene series, and between each line, you actually have one VA unit added. So let's say this is a pure polyethylene, maybe containing 0 VA unit. This one contains 1 VA, 2 VA, 3 VA, 4 VA, and so on. PE along the x-axis and adding VA step by step. So this is what I call a sequential processing, where I use these scaling plots as active interactive tools, not frozen pictures, but I make the plot, I select, I extract, I spread again, I rescale again, I select, I extract, I rescale again. And this way, you got that beautiful plot from that noisy mass spectrum. You can go even further, turning this plot into what I call a DP plot, which is displaying the number of E versus number of VA along the X and Y axis. And now you have the entire information that was kind of hidden in the mass spectrum. Number of VA, number of E, number of VA, you have all you need to know about your sample at a glance just by doing this sequential processing from the mass spectrum. Same idea here for a terpolymer, so 3 monomers. I got my mass spectrum, styrene, MMA, HEA terpolymer. I rescale in one way to separate the series by N groups and by isotopes. For example, here, that cluster here, I found that it corresponds to specific set of N groups and only carbon-12. I can select, I can rescale a bit differently, and now I am separating by C. So each cloud corresponds to has a different number of C units in the chain. That cloud at the bottom here contains only one C. So from a terpolymer to a copolymer, the points here, the composition is changing only by the number of A and B. They all contain the same number of C, 1. You can select this cloud and rescale. Now to separate by B, for example. So each line contains a different number of B units, and the line here. So the line here is a poly A, let's say, and then you're adding B one at a time when you go down along the plot. So I am turning that copolymer into a set of homopolymers. So that line is the homopolymer coming from a copolymer coming from a terpolymer. Just by rescaling, playing with that value of rescaling, I'm always using S to rescale, always styrene, my monomer A, but I change what the mass of styrene is in my reference, in my new basis, and that helps me spreading, separating, extracting information, simplifying the data step by step from a noisy mass spectrum, denoised here, to get a terpolymer, to get a copolymer, to get a homopolymer. So far, it was only MALDI MS data, which means only single charging. But I want to show also a bit of ESI data too, which of course will lead to multiple charging for polymers. Okay, this is an example of ESI HRMS of PPO, and you can see that you clearly have multiple charge states here, right? And many of them tend to overlap in the mass spectrum. The good thing of this plots for ESI is that they actually reveal the charge state at a glance. Just because of this difference of spacing between isotopes, what if you have a +1 polymer, you have one mass between the carbon 12 and carbon 13, very basic. If you have a +2 or -2, you will have a 0.5 mass difference between the carbon 12 and carbon 13 one. This is how you evaluate the charge state of series in a mass spectrum. Well, this splitting, this mass difference is reflected in the Kendrick plot through this split of lines. Series at charge state 2 plus or minus 2 will be seen as two lines in the plot. One line here, that's a plus or minus 2. Well, they're all plus here, so let's go for plus. I got 3 lines here, 1 line, 2 line, 3 lines. That's a +3. I got 1, 2, 3, 4 lines here. That's a +4. 1, 2, 3, 4, 5. That's a +5. 1, 2, 3, 4, 5, 6, +6, and so on. So just generate this map. That's the most basic rescaling. PO 58.0418 goes to 58. Static rescaling, and count the lines, and that will give you the chart state of the series. 2 lines +2, 3 lines +3, and so on. First step. Second step, I want to know more about this +3 series here. What am I doing? Well, I'm using this definition of conic mass, and I regroup the +3 series into one cluster only, using this Z value here, the Z parameter here at 3, set at 3. This is canceling the split of the +3 series, and these 3 lines are merged into one group here. Only one cluster of points contains all the +3 series. That's the second step. And the third step, I rescale another way. For example, here I'm using 867. You can see like I can go very, very far from the initial mass, right? PO normally 58.0418 in ILPAC scale. I say that it becomes 867. So that's really, really far from the normal mass, but it works because doing this rescaling, it leads to a massive expansion of the points along the y-axis, and that's revealing that I have 1, 2, and 3 series at +3 in my spectrum. So from this mass spectrum to these plots where I see, oh, I have a +3 series here, I group them into one cluster and I re-separate them differently to visualize them, to highlight the number of series, like to see the series individually. And then here you can select that cluster of points and you can extract the peak list to assign the M/Z if you want. So you're able to extract a targeted chart state in a targeted series out of this mess just by playing with the rescaling, always using PO, but rescaling PO to different values. So the whole thing works also for ESI and multiple charging. And the whole thing works also for MS. So far, I've shown only MS data, only MS1, single stage. But these plots, these Kendrick plots, are also useful and I think not used enough for MS. It's a very, very nice way to display MS data because MSMS of polymers will also show series. You also have series of fragments that are spaced by a specific moiety. So the Kendrick plots of MSMS spectra will also show alignments that will help you either assigning MSMS series or labeling series. This is a fun example here. This is the MSMS of a copolymer that has been made very precisely to contain a message, to contain information. It is a copolymer containing two monomers with a difference of CH2 in the mass, methylene or H here, and they are assigned as bits 1 and 0. Depending on the way you arrange these monomers, the order that you add the monomers to the chain step by step, you can store a message, you can store a binary message in the copolymer, in the chain. In that case, that chain here is storing the information 0001101101101001011. That's my message, which is stored in this copolymer. To read this information, you're doing MSMS. You're activating, you're fragmenting that copolymer to detect the fragments and assign them as being 1 or 0. But you can do this graphically if you want. Just transform this mass spectrum into its Kendrick plot. This is the Kendrick plot using the bit 1 or the bit 0 as the rescaling unit. And you can see that you have a nice alignment here, kind of a stairway-like plot. And that plot is actually showing the code graphically. Just start from the first the precursor ion and go down, and you can read the message. Here I'm rescaling with 0. So the bits 0 are aligned horizontally, and the bits 1 are obliquely aligned. So starting from the precursor, you go to 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, 0, 0, 1, 0, 1, 1. That's my message here. You can do the same thing if I'm rescaling by 1. So now the bits 1 are aligned horizontally, and the bits 0 are aligned obliquely. Start from the precursor ion, 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, 0, 0, 1, 0, 1, 1. That's my code here. It works. So at a glance, you can graphically read the message stored in this copolymer, which is revealed by MSMS, but read by this kind of plot. Another, I think, interesting application of the plots for MSMS is just to simplify the labeling, to simplify the reporting. I published that MSMS of PDMS a long time ago. This is for, I think it was, yeah, like some kind of doubly charged methyl ended PDMS. You got this interesting mass spectrum, and to assign the peaks, to label the peaks, we had to make this very annoying figure with some insets. You have to zoom in, and you have to assign the peaks using all these letters. It's quite of a mess and a hell to be able to convey the information about the peak ID for this for this MSMS spectrum. There's just too many peaks. Many of them are very low abundance, so it's quite hard to simply convey the information in a paper. Instead of doing this, instead of doing this figure and going and using insets and everything, just make a Kendrick plot. This is the Kendrick plot from that MSMS spectrum using DMS to rescale, and I said that DMS, which is normally 74.0188 in the AirPack scale, becomes 73. Just one plot, you can easily separate the series. You have a series here, one here, another one here, etc. And only one label is enough, only one figure and one label per series is enough to assign the whole series. You don't need to use this in sets. You don't need to assign every peak individually. You can assign a whole series at once using only one labeling. So I think there is really something to do here for the reporting of MSMS data in papers using these plots. That should really simplify the way we report data, the way we show data in conferences or in papers. So instead of using these complicated figures with so many labels to add, it takes a long time to just do the figure. Here it takes a second to generate, and you can assign a whole series at once with only one label. If the plot looks a bit fuzzy, that's because, again, my mass spectrometer lacks a bit of accuracy because the peaks are of very low abundance. So the shape is not very well formed. So the accuracy is not very high. So some point alignments are a bit fuzzy here, clearly. You can see it's very wavy. To avoid this problem, you can actually you can again rescale the data using the dynamic definition a bit differently. I don't use a value like a 500 or 70, whatever you want to rescale. I'm using 1 here. So I said that my 74.0118 in Arabic scale becomes 1. That has been called remainder. It has been called MARA by other authors. It's all the same concept. You simply say that your mass of this monomer 74.0188 becomes 1. It's like an extreme rescaling. Doing that, again, it's so extreme, you're expanding so much along the y-axis, it looks like the points are lining up more horizontally. It's visually improving the point alignment along the x-axis. From this plot here to that plot here, look at this series here, this TMES B plus ammonium. It's wavy here. Those two are beautiful straight lines in that plot. This MEZ series here, it's really wavy in that plot. You have a beautiful series of line here with almost no more variation from one to another continuum. So that rescaling, that specific rescaling 1 leads to this very beautiful plot with a clear straight lines. Again, because of such an extreme rescaling, the points are spread so much along the y-axis and then just folded step by step, folding. It leads to these beautiful straight lines. It's a nice way to visually realign points when you have this little lack of accuracy and resolution in your data in the normal plot. Another application of this remainder concept, this is the MALDI HRMS of a PCL, but in pretty high mass range. We are in the 12,000, 20,000 Dalton range here. So of course the mass spectrum is pretty congested, and the static plot from that mass spectrum is also quite useless. You have this big reddish blob here. It's really hard to make anything out of it. You don't even have any alignment, just because, again, you see like the shape of the pattern here. You are at the limit of resolution and accuracy of the system. So this plot is not very useful. If I'm using a dynamic plot, so I'm rescaling my PCL, not 114, but 113 now, you have a separation of series. So here you can see that you have at least 4 series of PCL in that mass spectrum. So there is a gain of information. There's a gain of understanding from this to this to this, but still the whole thing is slightly oblique. It's very fuzzy. It's hard to make anything out of it. So go the whole way down to 1. I'm rescaling my PCL from 114 to 1. That's the remainder plot. And that leads to this beautiful plot, which displays straight lines, and it's revealing that you have at least 6 series of PCL, not 4, not 1. but 6 of them. You even have +2 ions here. This is actually beautiful. In a MALDI MS data, you have a +2 ions here. You probably have some fragmentation occurring in the low mass range. So you have a lot of information revealed at a glance from this plot versus this, or versus this. So again, this concept of remainder rescaling down to 1 leads to an extreme expansion of the mass defect along the y-axis, and that leads to this nice straight lines, which improves really clearly the amount of information that you get. Ah, c'est pas bon. Putain, fait chier. Je fatigue un peu là. And another application of this remainder of this extreme expansion for a linear TOF. This is the MALDI TOF MS of a PCl in a linear mode, so low resolution. You can see this blob here. There is no more resolution of isotopes. You have only this ugly Gaussian peak, which is containing all the isotopic peaks of this PCl chain. Of course, the kinetic plot from that mass spectrum is far from being useful. You have this completely fuzzy oblique. There is nothing to do out of that, just because there is no resolution, there's no accuracy in the data. But if I'm using this remainder concept, so rescaling PCl from 114 to 1, you now have beautiful straight lines, and you can again see 1, 2, 3, 4, and maybe 5 and 6 series here. So even with the linear TOF data, with the lowest, the poorest resolution accuracy possible, you can still create interesting maps, useful maps, carrying information using this one rescaling. Very briefly, I haven't shown much of LC or GC data sets. I mean, hyphenation so far, it was only MALDI or ESI infusion. It's already a long talk, so I'll stop very soon. Just very briefly, what you can do using these plots for LC-MS data, you typically have two situations, two cases when you analyze a polymer by LC. It's either all the congeners are co-eluting, so all the chain lengths are behind the same peak. You have one LC peak here. You get the mass spec from that peak, and you have all the chains at the same time. So the plot is giving you this beautiful alignment. You can here you have clearly, you can tell, okay, here I have a PEO series behind that peak because I have my PEO alignment in my kinetic plot using PEO as a rescaling mass. So you can ID that peak as PEO. Or the second case you may have is that the LC method, your column or your gradient, is separating the chain length length by length. So each you have one chain length for each peak, each LC peak. That's the case here. I think, yeah, this is a PDMS. So each peak here is a different chain length of the PDMS. The plot is still useful here because what I can do is the so-called mass defect filtering, which is actually fractional mass filtering. I can get the mass spec and the kinetic plot of that peak here, and I can extract. I can ask a program to extract all the peaks, all the mass spec peaks that have the same fractional mass as this one here. And that's a way to generate a beautiful EIC from that noisy TIC. So you can clearly see the blue line here. Those are all the PDMS chains that share the same fractional mass. In other words, that share the same N group and the same adduct. So it's a nice way, easy way to generate EICs and to potentially extract polymer series that are LC resolved. Finally, a GCMS example to cover all the topics I was supposed to. This is the GCMS of a rubber extract. And we were actually, we had to tell if this rubber contain halogens or not. And this is something we can actually do easily, again, using these plots, using these Kendrick plots. This is the mass spectrum and the Kendrick plot for that peak here, using CH2 to rescale. It's rubber, so we are expecting hydrocarbon chains. You got that plot here. That peak, I got that plot with clearly another group of points above the main one, which is absent here. And from that peak, I got that plot with this second cluster of points, which is absent here and absent here. So at a glance, using it's pretty hard to differentiate the mass spec. The mass spectra are different, but you cannot tell if it's containing any CL or BR species. At a glance, it's hard to tell. Using the plot, at a glance, you can see that you have one stuff here that are unseen in this one. So this is different from this is different from this. And if you know a bit your mass defect, you know that this little cluster above the main one is actually chlorine containing peaks, and this cluster is bromine containing peaks. Okay, the mass defect or the fractional mass of bromine is even lower than the one of chlorine. So the space between the two CH only and CHCl is small, but between CH only and CHBr is higher. So once more, graphically, I don't need to know the values of M over Z here. I don't need to display the labels. I can graphically show that this peak contains bromine, this peak contains chlorine, and this peak is only CH, is a pure hydrocarbon peak. And even better, if you look at that cluster of points here, you can also tell if you don't know the spacing between bromine, chlorine, and CH, if you don't know the spacing here, just look at this cluster here and rescale using bromine or chlorine isotopes. There's something I like to do, a little trick I like to do. Rescaling that plot using the difference between chlorine 37 and chlorine 35, you got this tiny, slightly oblique alignment. So this is no chlorine containing peak. If I'm rescaling using the difference between bromine 81 and bromine 79, that line lining up horizontally. So those guys are isotopes of bromine. So this cluster here is a bromine containing peak. So this peak contains bromine. Right? Like a very simple trick. Again, completely graphically based. There is no value, no numbers needed here. Just look at the pictures, play with the rescaling, and you can get a hell of information out of this data, either GC, LC, or MALDI infusion, etc. All right, so I think I've been already very long for that talk, so I'll stop here. Just I try to show a bunch of examples of application, trying to explain the few concepts about this mass defect, fractional mass, rescaling, static dynamic. I hope it was clear enough. If you have any questions, comments, ideas of things to implement or things to do to improve, please send me an email about that. The main takeaway here is like just use these plots. There are many programs available out there to make this plot open source, freeware, commercial programs. There's a bunch of options. If you don't know, you can ask me and I can give you a list of programs available from manufacturers, from labs and so on. There are really many options available out there now. So please try this plots. Try this plot um, infusion, for LC-MS, for GC-MS, for IMMS, for MS-MS too. It's useful for MS-MS, for any type of MS that you have. That it can be ESI, MALDI, DART, whatever, PyGC. There is a usefulness of this plot for every single type of MS analysis, I think. Really, I think that. And also, a very important thing, do not look at these plots as frozen pictures. Again, if you use the good program, if you use the some of these nice programs available out there, you should be able to use these plots as dynamic, active tools. You can select data, extract them from the plot, process them differently using other values, other rescaling units, other rescaling factors. So use these plots really as filtering interactive tools, not only as a frozen picture put in a paper. It is used as a filter. It is very useful to remove the noise, to remove the isotopes, to remove the unwanted signal, to extract a very tiny piece of information which may be really completely buried or hidden in the initial data. I think that's also one of the most interesting part of this plot is being able to reveal tiny amount of polymers in a messy spectrum and extract it, to process it, to assign it, to ID it. So just this filtering capability is I think essential, and that's the main application of this plot for me right now, is being able to extract this tiny signal of a polymer from a messy, noisy mass spectrum. All right, well, thank you very much. And again, if you have any questions, if you have any comments, please send me an email and I'll be glad to answer you. And of course, I forgot this last slide. Well, I guess you all are already members of our interest group, but in case if you're not, feel free to join the group. You can send me an email to be part of the mailing list. We have a page on the ASMS website in the member section where I'm trying to post some content to. We have a LinkedIn page where I'm trying to post some content or post some announcements. Feel free to post. If you have anything you want to share with the community, please feel free to send a message or to post to submit a post. And I also have a bunch of stickers left. So the next time we meet in person, I guess at the ASMS, ask me if you want to have a small sticker to promote the group within your lab. All right. Thank you very much.